So in this video, we're going to talk about the division algorithm, which is also a theorem. But the proof basically doubles as a blueprint for an algorithm that you would, you could program in Python, and maybe I'll make a bonus video of writing out this algorithm in Python. But basically, it's just a formalization of the intuitive process we have of being able to divide a number. So given any two integers, you can always, perhaps they don't divide into each other evenly, but you can always write it as a quotient with a remainder. So let's make this formal. So the statement of the theorem is that for all positive integers, a and b, and really this works for any integers, but the proof will just be a bit cleaner for positive integers. And we're going to assume that b is not equal to 0, because we're basically going to describe dividing a by b, and we can't divide by 0. There exists unique, so by this exclamation mark I mean unique, integers q and r, such that 0 is less than or equal to r, which is strictly less than b. And then we'll have that a is equal to b times q plus r, which is going to be our remainder. Okay, so let's prove this. So consider the set which starts with a and goes to a minus 1 times b. So a could also be viewed as a minus 0 times b. So a minus 1 times b, a minus 2 times b, and we're going to keep going. So subtract every possible multiple of b from a. Now, this set has to have, so clearly, eventually this will be negative. Eventually, if we multiply b by a large enough number, we're going to get an element of this set which is negative. So, for instance, since b is a positive number, for instance, if we had a minus a times b, that's certainly going to be less than 0. But we do know, so eventually it's negative, but we do know a for sure is a positive number. So somewhere in here there's going to be the smallest positive element. So basically the last multiple of b before it becomes negative. We're going to call that q. So let a minus b times q be the smallest positive element of this set. Now, it's going to turn out that this will be less than b. And to see this, suppose, to the contrary, that a minus b times q were larger than b. Well, then I could subtract b from both sides. So this would be a minus b times q minus b. This would be greater than 0. And then just rearranging things a little bit, I'd get a minus q plus 1 multiplied by b would still be positive. But now notice this, a minus q plus 1 times b, this is a smaller number than a minus b times q. But we assume that a minus b times q was the smallest positive member of the set, and we found another member that's even smaller and positive. That's a contradiction. So we know it must be the case that a minus b times q is less than b. And we know also that it's non-negative. So I suppose up here I should have said let it be the smallest non-negative element, because it's possible that it could be 0. So in this case, we've already figured out what our q is, and so we're going to notice that this element meets the criterion for our r, that r is at least 0 and smaller than b. And sure enough, if we take r to be a minus b times q, observe that now b times q plus r would be b times q plus a minus b times q. Well, the two bq's cancel out, and this is a. And that's exactly what we wanted in the statement of the theorem, that a was equal to b times q plus r, and that's what we have down here. Okay, so we need to show one other thing in this proof, and that is that q and r are unique. So suppose we had some q, p, r, and s in Z, where both r and s are at least 0 and strictly less than b, where b times q plus r is equal to a is also equal to b times p plus s. Now, both of these quantities are equal. The leftmost chain of these equal signs and the rightmost term of these equal signs. So I can subtract one side from the other and get that b is equal to b times q plus r minus b times p minus s. And then this becomes b times q minus p plus r minus s. So then, I can now move this over here to the other side of the equation. So I get minus b times q minus p is equal to r minus s. And now notice the left-hand side of this equation is divisible by b, because we have this b right here in the factorization. And so the right-hand side of this equation must be divisible by b. However, because r and s are both between 0 and b, we know that r minus s, well, it must be strictly larger than negative b and strictly smaller than positive b. But if we think about the multiples of b, the only multiple of b that lies in between negative 1 times b and positive 1 times b is 0. So it must be the case that r minus s is equal to 0, or in other words, that r is equal to s. So we have that the remainders were actually the same all along, but then plugging this back into our formula up top, this tells us that b times q plus r is equal to b times p, and we can now replace s by r. And then subtracting r from both sides of the equations tells us that b times q is equal to b times p. And finally, we just divide both sides of this equation by b, because in our assumption, b is not equal to 0. And we get that q is equal to p. So in fact, these two separate ways of writing a must have actually been the same all along. And so now we've proved the uniqueness. Okay, so that concludes the proof of this theorem. And we're just going to follow this up with one little lemma that's going to be useful for the next video. And that is, so, lemma. If A is equal to b times q plus r, then the greatest common divisor of a and b is equal to the greatest common divisor of b and r. And we're actually we're gonna see that this paired with our division algorithm in the next video is going to help us prove the Euclidean algorithm, which gives you a systematic way to determine the greatest common divisor of any two numbers. So let's go ahead and try and prove this lemma here. So we're going to let D be the greatest common divisor of a and b. And, well, that means, by definition, that D divides A and D divides B. So if we rearrange our equation up at the top, we get that A minus b times q is equal to r. And, well, D, since it divides both a and b, it divides the left-hand side of this equation. And so it must also divide the right-hand side of the equation. So we know that D divides b and that D divides r, and therefore D is a common divisor of b and r. Okay, so now we're going to let C be any common divisor Okay, so we're going to let C be any common divisor of both b and r. Then by our above equation again, since a is equal to b times q plus r, r divides, well, c divides and since c divides both b and r, c must divide b times q plus r, which we know is equal to a by our assumption, and therefore c must also divide a. But d is the greatest common divisor of a and b, and since c is a common divisor of a and b, that means that c C must be less than or equal to D. So what did we show? We've shown that if we take an arbitrary common divisor of B and R, it must be less than or equal to D, and therefore D is in fact the greatest common divisor of both B and R. And that'll do it for this proof and for this video. See you in the next one.